Okay, so as Mark introduced, I will try to show you that in the domain of material appearance, we are at the frontier or in between physics and perception. And the difficulty is that, of course, we know some attributes, color, shape, gloss. Okay. But most of the time in the real situations, these attributes that we study separately are combined, and these bring more difficulty in studying them. So I will try to illustrate that with a few examples. But as material appearance is not so well known by everybody, I prepared a short introduction to just explain what we are talking about. So, of course, material appearance is a crucial issue in many industrial domains, and not only industrial, but if we think in cars, outside, inside, in cosmetics, in jewelry, or even for tomatoes, we have been asked by a company who sells some seed, and it was strategic for them to prove that the gloss of their tomatoes was better than the one of American manufacturers because appearance, for example, is related to quality. And then it makes the products attractive and so on. This is one of the challenges with appearance. There are many other ones. But it is a complex scientific problem that we try to address within the grouping of research at PAMAT that I have the pleasure to lead. Appearance, what it is. If we have a look on the definition, the official definition that has been given by the International Electronical Commission, it is the aspect of visual perception through which an object is perceived to have attributes such as size, shape, color, texture, gloss, transparency, and opacity. I have been told that that definition, that is very large, imprecise, is the product of tens of hours of discussion, right? Actually, it is difficult because appearance is a sensation or a set of sensations, something that is produced in the brain. So by definition, something that is impossible to measure, physically at least. Okay, so that is the difficulty, and it is also why there is a part that is subjective, and it is very difficult to define it in a scientific way. But fortunately, that sensation is related with something that we can measure, with a physical quantity that is a light signal. And now today, we have some tools to measure a light signal, thanks especially to imaging. Okay, so appearance is related to perception, something that happens in the brain. The question that we could ask is, to which extent we have a sensation that is enough reproducible to do science with that? Okay, so for example, there are several levels. If someone look at an object like that, I think that we can agree that this is a vase. It is rather spherical. It is green. I think we all agree that it is green, okay? So it is reproducible. We can do science with that. Is it beautiful? Maybe we don't agree, okay? So this is something else, maybe related with, I don't know, human science or just subjective, okay? So this is related with perceptual science. On the other side, we can replace the observer with a camera just to record or to capture the light signal and try to find some correlations between the light signal that we can measure and perception that we can assess, okay? And material appearance is based on this relationship between perception and measurement. In optics, and this is my specialty, we are focused on what happens regarding the light signal between the light source, the object, and what enters into the eye, okay? And what I will tell you today is based on that, not on the perceptual aspect. So the light signal, we can use some models to predict it or instrument to measure it. And we are often also interested in using either prediction model or measurement to assess the object, the material in itself. Regarding the attributes, this is an image I prepared when it was the Cannes Festival. And we have the different attributes that are represented here. For example, the color, which is related with the spectral variation of light. Translucency, which is related with the geometrical variations of the light signal. For example, we understand that trousers are transparent because there is a correlation between the color of the squared area and the fact that there is a leg. Sorry. Yes. Okay, yes, here. We understand the correlation between the color here and the color here, and we understand that it is translucent. The same for gloss. Okay, here we understand that it's glossy because we see that the carpet is reflected. We understand that here probably there was a light that is reflected in that. So we understand that it is glossy because of a global understanding of the object. Excuse me again. Yes, of the object and the surrounding. And spatial relation, we understand that there is a texture here. Okay. And of course, the shape, we understand that it is shoes and legs and so on. Okay, one word about color, so related with the spectral variation of light, over the spectral distribution of light. Okay, so from a spectrum like that, we have models that can tell us that it is a magenta color. And color is the more advanced attribute on a scientific way, thanks to the works by the CIE especially. So we have equations like that. The color problem has been turned into equations where we can relate the physical quantity, so a spectrum, with psychophysical functions. And at the end, we have perceptual values. So the correspondence between the measurable quantities, the light quantities, and perception has been done, okay, with some limits. I don't enter into the details. Something important, because I will come back to that. These equations mathematically are the projection operator. So it means that spectral function is turned into three coordinates. We lose the spectral information with color. We have only three values. And the other consequence is that different spectra can be perceived into the same color. For example, with a RGB projector, we can produce some yellow even though there is no yellow light. Okay, this is what we call metamerism. I will come back to that a little later. Okay, but color is, well, the color science is still limited. The color models are well adapted to objects that are matte, opaque, flat, uniform. Okay, we are more advanced model for more difficult objects, but basically, basic color science is related to well adapted to describe the color of that book, but more difficult if there is a texture or translucency on the object. Glass is not well advanced, not as advanced as color. Okay, the understanding of perception, the correlation between the light signal and what we see is still a subject of investigation. Okay, so we have here some examples between matte and specular, the different grades of glass. Usually, glass is, it is related with the reflection of light at the surface of the material, and usually the glass is not colored. Okay, here gloss is white, for example. But that's not always the case. I will come back also on that. Okay. An example where glass can be confused with color, with the example of the painting of Pierre Soulages. We have the illusion that this paint is gray, but actually we have here only black paint. All the materials are black, but only the surface reflection. I have just a small drawing to fix the ideas. Here we have, in some parts we have smooth surface, and some parts we have rough surface. If we illuminate that with collimated light, on the smooth surface, all the rays are well organized, okay? And either we are in the direction of these rays, we see white, or out, and we see black. Okay, so it is black and white depending on the position of the observer. When it is rough, we can rotate around the surface. It is always gray because we always have a small amount of light. Okay, so this is what we see here. Oh. Here it is black because we are not in the specular direction. Here we are white, and here it is rough, we see gray. Okay. Other example, here with some objects that we rather well know, we see the reflection of the scene of the room on the surface of that ball. Okay. Here we also see the reflection of the room, but it is blurred. Okay, so we understand that this is more glossy than this, and this is more satin. We see some reflection, but the room is not reflected. We don't have a sharp image of the room. And I don't have example here of matte ball. Okay, so glass, we say that it is a second order attribute because it is a correlation between what we see on the object and also what we know of the room. Okay, so we need to recognize the reflection of the room on the object to understand that it is glossy. Another possibility, I cannot show you here on that image because it is a still image, but with a video, we can see that if we move and that reflection moves also in correlation, we understand that it is gloss, the object is glossy. Okay. The color is three-dimensional. It is known for 2,000 years, no, 200 years. Glass, we still don't know. So it has been proposed that it could be, well, 5-dimensional, but we are not sure. Okay, we don't have standard scales. We don't have models. One scale has been proposed for some black objects with a gloss meter. So the gloss meter will send a beam of light, and if it is a black polished surface, all the light will be reflected in that cone, and we say, let's say 100% of the light will be, well, no. All the light is in that cone, and we say that it is 100 gloss unit. And if the surface is rough, it will be less. Okay, so it is the gloss scale. That is the only scale that we have today for glass. So we have some low-cost instrument, glass meters. We have some scales that here it is not 100, but maybe 80 glass units. This is maybe 5 or 6 glass units. So we have standard scales. The problem is that it is only adapted to matte, opaque, flat, uniform, and black surfaces. And in the real life, we have objects that are not flat, that are not black, that are, that have a shape, color, and we combine all the shape, color, glass information together to feature the appearance of the object. So that is the main problem. We have correlations between the different attributes. For example, here we have a book in two finishings, coatings, one that is matte, one that is glossy. The color printing, the color that is printed is the same, but the gloss finishing makes a difference because, well, it is for the same reason that the soulage painting was gray when it is rough. Okay, so it is a bit lighter. Okay, so a change of gloss can induce also a change of color. Other experiments have shown that the shape can also affect the color perception. For example, that object, what would be, this object has the same color of one of the patches, but which one? So it is exactly the same material, the same finishing, but in one case it is flat. In one case it is, well, cylindrical. And, well, it is difficult. Maybe it is this one or this one, we don't know. Okay, so after this introduction, I wanted to show you three topics where we have two attributes together and over examples on which we worked or we are working in the Hubert Curien lab. So first, interaction between shape and gloss. I explained to you that the gloss matter is adapted to surfaces that are flat. And we have examples of objects which are not flat, especially the Pierre Soulages painting. We are working with one of the official art restorer of the Soulages painting, the Soulages artwork, Pauline Elou de la Grandière, because some of the painting of Pierre Soulages are degrading because of the quality of the paint. In the 60s, there was a batch of paint that was of poor quality, and the painting is becoming liquid. Some matte parts are becoming glossy, or the opposite. Okay, and it is very difficult to follow that in time. For when the color is changing, we can take some pictures, color pictures. But with gloss, it is very difficult to make accurate imaging and to follow in time what are the evolution of these degradations. So here you can see all the parts that are followed carefully because they are changing. Every 6 months it has varied, and so it's damaging very fast. So we need an imaging technique that at least can store, can record what is the state of the painting. The problem is that we cannot use a gloss meter because we need to have something that is portative. Well, the gloss meter is portative, but we need to have a contactless instrument. We cannot touch a painting, and we need an instrument that is adapted to non-flat surfaces. Okay. So this is the purpose of something that we want to develop. We have started with some student project in the 3 past years. The idea is to use a moving light and a video camera. So I will try to show you, not with a Soulages painting, but a piece of laser. Okay, so a light moves. It makes a reflection that moves, and we store that. Okay, in each pixel, we look at the variation. Okay, the variation of gray. Okay, so in each pixel over time, we have a variation of the gray level like that, and depending on the width of that curve, we have an indication on the glass. So this is the idea. And the advantage is that if the surface is not flat, okay, but it is locally curved, in the corresponding pixel, it just induces a shift of the curve, okay, but still something that we can analyze in terms of glass. So this is the idea. We have done in January last year some preliminary tests on that painting, which is in the Museum of Saint-Étienne, over that area, and we have a first gloss map. So here it is a color picture. On that picture, you cannot see what areas are matte or glossy. Okay. On a black and white picture, well, it is the same, we can see. Whereas here, we clearly see that these areas are glossy. Glossy is black in that image. So this is glossy. Okay, here also, we have some gloss. Whereas in that area, it should be matte. Okay, so we are here in a part that is damaged, which is not visible here. Okay, so this is an incoming project. We will work on that in the coming month. Second example is light inter-reflection, something that on which we have worked together with Damien Muselet and Alain Trémaux in the past. The fact that we have an interdependence between color and shape. Usually, when we analyze the color of a surface, we take a flat area. But on a dress like that, we have concavities in which the light is not reflected once, but reflected many times. Okay, so here the light is colored, let's say, more time because it is reflected many times. It is the same here. Actually, here it is gold. But the fact that the light is reflected multiple times makes the appearance of gold orange, whereas in our idea, gold is yellow, not orange. Okay. So it is something that we can find in many, many objects. Each time we have some concavities in the object, and it changed the color appearance of the material. So this is something that we can model. Don't show you the detail, but we have an analytical equations for that. And the interesting point that has been used by a PhD student, Radadeb, is the fact that we can relate what we capture with the color camera, the illumination, the reflectance of the object, so the spectral property of the object, and the shape. And reversely, if we take a picture of an object with known shape but unknown spectral reflectance, okay, there is only one parameter that is not known, we can recover it. That is interesting because this is an RGB picture. I said that RGB color, we have lost the spectral information. But thanks to that shape, actually, here, I don't know if you see that, no, the color is not good. Actually, due to interreflection, there is a color gradient that we don't see here. We see it on my display, but not yours. Okay, so actually here, there is a color gradient. So a gradient of RGB values that contain all the spectral information. And this is what we see here. In blue is what we can measure with a spectrophotometer. In red is the spectrum that we can recover from this RGB image, thanks to the model. Okay, that is very interesting. That technique coupled with machine learning, we can, from an image like that, estimate the spectral properties of the object and the spectral properties of the lighting at the same time. Okay, so from an image, we can get many physical information from the object. This is also something that we have analyzed in the second PhD for the consequence of interreflections. Here we clearly see the color gradients in the V-shaped concavities and the consequence on the appearance of objects. One funny consequence is that with perfectly white surfaces, for example, snow, we can see the shape of the object if we are under direct light, but not under diffuse light. So here we see, we don't see any relief on the surface. Okay, so the color of a flat surface, and we try to fold it and more, and we see that the color turns from magenta to reddish. Okay, just by folding like that. Other consequence, if we have two flat surfaces that have the same color, metamerism, you know, you can have different spectra and the same color. This is for flat surfaces. Now, if we fold these surfaces, well, the fact that they don't have the same spectra, they don't have the same color gradient. Okay, so we can have two surfaces that are, when they are flat, they have the same color. As soon as they are not flat, they cannot have the same color. Okay, that is, metamerism is impossible with shaped surfaces. We also studied that with metallic surfaces. So here we have two gold mirrors facing each other, and we see once again that this is the color of gold that we know, but when the mirrors reflect themselves, the color turns to orange. And this is something that also can happen in a ridged surface. Okay, and this is also something that we can model. We can analyze the spectral properties of the ridged surfaces, the color properties, and again, some examples. In copper, that's funny. We see that the copper can become clearly orange or red when objects are reflected multiple times on each other. And silver can become clearly yellowish. This is not golden, it is just multiple reflection of silver. Again here, it looks yellow, but it is silver with multiple reflections. And the last point, if I have still a few minutes. Excellent. So another example of combined attributes. Here it is gloss and color with examples where the gloss is colored. And it is something that happens especially in inks. Every material that is strongly absorbing in one specific bandwidth, and the refractive index varies a lot in the according to the wavelength, and it gives us some, well, colored reflections. So for example, cyan, which looks cyan when it is printed on white, but when it is printing on the black background, we see only the surface reflection, which is reddish. For magenta, it is orange. For yellow, it is bluish. So, well, there is not an easy understanding correlation between the gloss color and the diffuse color. Other example, this is just big ink, you know, the ball pen ink. This is inkjet. So we see different colors, the gloss. And I show you an example that is, this effect has been used by a student in the art department of the university. So it was an inkjet image printed on paper. She washed it with water, and all the black ink disappeared. Okay, so we see that the black ink disappeared. And when you look at it, well, the reflection on the window on this, the inks are more glossy than the nude paper, and we recover the original image. So we have a sensation of negative positive by using this glossy effect. So I have a video where maybe it is more easy to see. If it can launch. Yes. Okay, so we will see the reflection. Yeah. Yeah, and we see the positive image. And if we are out of the reflection, it is a negative image. And we have also used that, or another example, where we can have several patches, which are the same, which have the same color. So these two have the same color, these two have the same color, and so on. And when we look at the reflection, sorry, they can have different colors. So you will see it. So far, they have the same color, and here they have different colors. Okay, and this is something that we can use to create some gloss images. So here we have something that is that looks uniform, orange, and when we have a reflection, well, it is corporate. we can see an image. So it is a gloss image. Okay, so I come to the conclusion. All these physical and perceptual effects are, well, under our eyes every day. I think we have examples in many situations. They are a paradise for artists. Pierre Soulages has used the glass, but also there are the artist students. I would say a nightmare for physicists because most of the time it is very difficult to understand, or also a paradise because it is many interesting problems to cope in the future. I thank you very much for your attention.